Hello. In this video, we're going to continue on with our central atoms that don't have lone pairs yet. So just want to remind you, right, with this idea, we talked about the electron pair geometry, or let me make sure I'm using the right terminology. Yeah, electron pair geometry. Considers the lone pairs and the atoms, and then we have the molecular geometry. In this case, these are all the same when there are no lone pairs. So all of these ones in the previous video and this video, the molecular geometry and the electron pair geometry are the same because we have no lone pairs. We will get to the ones where we do have lone pairs, and these are going to be different, but that'll be in the next set of videos. So not for today's, for the videos for this class. Okay, so we've looked up steric number of 2, 3, and 4, and we saw that this was linear, trigonal planar, shaped like a triangle, as well as tetrahedral. But we have seen that there are, and this is going to cover everything that doesn't expand an octet, right? So you can only get up to 4 bonds if you are following the octet rule. But we did see in the previous chapter there are things that can expand their octet. And so in this video we're going to look at steric numbers of 5 and 6, things that have 5 and 6 bonds around them, not just up to 4. Okay, so what do we get when we have 5 bonds? And what sort of molecule is this going to be? This is going to be something like PF5. Right, so something in the third row of the periodic table, our central atom, surrounded by very electronegative elements. So if we draw the Lewis structure, it's going to look something like this, where they're all going to be, just fit 5 of these around, put lone pairs on all the fluorines. Right, so that's our Lewis structure. But this doesn't tell us how this is actually shaped in 3-dimensional space. So much like our tetrahedral geometry, this is now something to spread these electrons out. We need to figure out what's the optimal way to do this. And so this ends up being what we call a trigonal bipyramidal structure. So let me try and draw this, and then also show you a picture that hopefully will maybe help you visualize as well. So our phosphorus is our central atom right in the middle. We're going to have one of the fluorines is going to be pointed straight up, one of the fluorines is going to be pointed straight down, and another one will be at 90 degrees to that. All right, so these are all at 90 degrees. But our other 2 fluorines are going to be one sort of pointed backwards and one coming forwards. So unlike our previous ones, we actually have 2 different bond angles in this one. So we have the bond angle between these fluorines pointed straight up and down. These are ones that we call axial. So this one up here and this one down here. You can imagine this is along the axis as if we drew like this was a sphere. And then these 3 fluorines here are what we call the equatorial, in the equatorial positions, because it's like they're on the equator that goes around this structure. So anyway, the angle between the axial and equatorial fluorines, in this case, is 90 degrees, and between the 2 different axial fluorines, so the angle from this fluorine up here and this fluorine down here, this angle is 180 degrees. And then the angle between our fluorines that are along the equatorial position here, so like right here, these are all 120 degrees. So this one as well, and this one as well. So this is the trigonal part, right? So this is why it's called trigonal bipyramidal. The trigonal part is the equatorial fluorines, or whatever molecules you have. So this is specifically our steric number is equal to 5, again with no lone pairs. We have our 3 equatorial ones are 120 degrees apart from each other, like the trigonal planar one when we had steric number of 3. But then we add sort of onto that the linear ones, one pointing straight up, the axial fluorine, and one pointing straight down. Okay, now if that was a little bit confusing, I've got an alternative way of showing this. And the name for this comes from the fact that this sort of looks like a pyramid. So I'm going to try and draw this without all the letters in here. But you get this sort of triangle shaped, and then you have a pyramid pointing up and a pyramid pointing down. And those are the bipyramids, right? So there's two pyramids involved in this. Let's see if I can pull over this. Yeah, this is the one I want. Right, so the same picture. Oops. No, I do want that. Come back. Just got to push the right button here. There we go. So here's our trigonal bipyramidal structure. And now I want this so I can pull this over. Great. Excellent. Okay, so this is what I was trying to draw. You can tell me whether I succeeded or not. But again, our 5 atoms, our 5 fluorine atoms, are represented by these dots here. Right? And so we have 2 of them that are, one is pointed straight up, one is pointed straight down. Those are the axial. And then these 3 along the equator, again, imagining these fluorine atoms as being on a sphere. If we rotate this so that we're now looking along the axis, we can see that we have this trigonal structure, right? We have this equilateral triangle in the middle. And then we have one pyramid pointing up and one pyramid pointing down. Okay, so hopefully you're able to visualize that. Our final, for today, our final structure we're going to look at, geometry, is something that has 6 bonds. So Sn equals 6. Again, no lone pairs. So for today, we're not going to worry about lone pairs, but we'll get there. And this would be something like sulfur hexafluoride, SF6. All right? And so what is the geometry here? So this geometry is what we call an octahedral geometry because it is shaped like an octahedron. If you're not familiar with what an octahedron looks like, I'll show you what it looks like. So it's very similar to the trigonal bipyramidal structure we were just looking at, except for now everything is all at the same angles. So there's no axial and equatorial anymore. It's all symmetric. So we're going to have our sulfur right in the middle. We're going to have one fluorine pointed up, one fluorine pointed down. And then we form like a square in the middle with the other fluorines. So 2 of them pointed back, 2 of them pointed forward. And this is our octahedral geometry. This is how I draw it. So all the angles here between adjacent fluorines are 90 degrees. So whether you're going from the top to the middle, and what you can view this as is sort of like a square between these 4 fluorines here. Maybe I should do that in a different color. A square that forms among these 4 fluorines here with another fluorine pointed up and another fluorine pointed down. Again, I'll pull over the optional way, the additional way of looking at this, where we're looking at it sort of on a sphere. And we can see, again, our dots on the sides here represent our fluorine atoms. So these dots here, 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 and here. And this is what an octahedron looks like. So it's this square shape in the middle that goes up to a pyramid on the top and pyramid on the bottom. So sort of 2 square pyramids pointed up and down. And then one thing I just keep forgetting to mention, there's a red dot in the middle. That represents our central atom. So that is our sulfur in this example here. Okay, and so this is the octahedral geometry. So if we have 6 bonds, this is the way to spread them out as much as possible. That's the goal, right? The goal is to keep the electrons as far away from each other as possible so that they don't have to be close and repel each other. And so when they push on each other, this is the best way to arrange 6 things around a central point and to get them as far away from each other as possible. All right. And so that's like the starting point of all our geometries. So this steric number 2 through 6, again, we have linear, trigonal pyramidal, tetrahedral, trigonal bipyramidal, and now octahedral for our 6. Those are our 5 different basic shapes that we're going to start with. And all of the examples we've looked at so far are with no lone pairs, where the electron pair geometry and the molecular geometry are the same. So our next step with this will be to now look at molecules, which there are many, that have lone pairs on the central atom and see how that changes things. And there our electron pair geometry and our molecular geometry will be different from each other.